Hi friends, in this video, what are the topics in our parallel operation? First of all, the first one is parallel operation of two alternators. This is the first topic. In this parallel operation of two alternators, first one at no load condition and second one at loaded condition. At no load condition, at loaded condition. In that, again first one, effect of excitation. Second one, effect of prime mover input. And in this, at loaded condition, the first one, effect of excitation. And next one, effect of prime mover input. This is the first topic in parallel operation. So we have to take four discussions here. We have four discussions here in the first one. And in second one, what is second one? Parallel operation of alternator with bus bar. And next one, parallel operation of synchronous motor with bus bar. Synchronous motor with bus bar. This is the next concept. Second and third concept. And even in this second concept, we have again two at no load condition and loaded condition. And even here also we have two at no load condition and loaded condition. And even in this no load condition, we have only one, that is effect of excitation. Are you okay? And here also effect of excitation. We have only one topic here. At no load condition, only effect of excitation. But here at loaded condition, we have two topics, effect of excitation and effect of prime mover input. Prime mover input, these two. And here also we have two topics, effect of excitation and effect of supply input. Effect of supply input. Right. These are the topics in our parallel operation. A very important concept. And to know this concept, we must know armature reaction. Without armature reaction, we can't do. I said you already. So now I am going to discuss the first topic in parallel operation, that is parallel operation of two alternators. In that, at no load condition and at loaded condition, what happened if excitation changes by constant prime mover input, and what happened if prime mover input changes with constant excitation. I will discuss this part of parallel operation now. Then after, I will go for synchronous motors and I will explain what are the topics in synchronous motors. Then after again, I will come here. Because these are comparable. These two are mostly same and these two are mostly same and these two are mostly same, just in reverse. So that's why first I will discuss synchronous motor, then after I will come for this parallel operation with bus bar. Are you okay? Getting my point? Right? Now our topic is parallel operation of two alternators. In that, at no load condition and at loaded condition. Are you okay? Very, very, very important topic in synchronous machine. The parallel operation of two alternators. Let's see here. I'm going to draw two alternators in parallel. For example, this is my first alternator and this is my second alternator. These two are operated in parallel. This is E1 and this is E2 and this is Z1 and this is Z2. If the current is I1 and here the current is I2, these two are operating in parallel. Here the condition for parallel operation is that the terminal voltage should be same. Yes or no? Phase sequence should be same, frequency should be same, and terminal voltage also should be same, then only we can make it in parallel. So here, for example, terminal voltage same, nothing but these EMFs also mostly same, because under no load condition, when no load condition there is no currents. If there is no currents, the terminal voltage is equals to E1 is equals to E2 at no load condition. Because at no load condition current is 0, then exactly E1 is equals to E2, that is equals to terminal voltage, then only it is possible. Otherwise, connect a voltmeter here or connect a voltmeter here. If the voltmeter reads 0 volts, then only we can close the switch and then only these two alternators operates in parallel. And see here, compared to terminal voltage, compared to or with respect to terminal voltage, this E1 and E2s are in phase to each other, in phase to each other with respect to load, with respect to load when we are talking. But when we are talking with respect to each and every alternator, nothing but, for example, this is plus minus, this is plus minus. So for example, this is plus minus, this is plus minus, nothing but see minus plus plus minus, nothing but with respect to each other these two are out of phase. With respect to each other these two are out of phase. With respect to load these two are in phase. Right, this E1 and E2s are equal. This is, I am talking at no load condition only. I am talking at no load condition. Two alternators are operating in parallel. At no load condition, here the current is 0. Here the current is 0. When current is 0, E1 is equals to E2, that is equals to Vt. With respect to this terminal, both are in phase, but with respect to each other, both are exactly out of phase. Both are exactly out of phase. This is E1 and this is E2. Now, what is my topic actually? Actually, my topic is effect of excitation when the prime mover input is constant. This is my topic. What is the effect of excitation when my prime mover input is maintaining constant? I'm not changing my prime mover input for both the machines, but I increased excitation of machine 1. What I said that I changed excitation suddenly. I changed my excitation of machine 1 suddenly. When excitation changes, we know the EMF is directly proportional to excitation. nothing but directly proportional to flux, nothing but directly proportional to field current. When excitation changes, then automatically EMF also changes, nothing but here my EMF is changes, that is E1 dash, for example, E1 dash. E1 dash is the increased EMF when excitation of the machine 1 increases. Nothing but here, actually both are same, both are equal, but when the excitation of the machine 1 changes, only the EMF will change. There is no change in phase shift, because we are not changing the frequency, we are just changing the excitation. So only this is increased up to E1 dash. When this is increased, then these two are not equal, these two are not equal, nothing but the E1 dash is not equals to E2. When these two are not equal, what happens, sir? Circulating currents or synchronizing currents will flows. Synchronizing currents will flows. What is the value of synchronizing currents? This E1 dash minus E2 upon Z1 plus Z2, where the circulating currents are like this. This is my circulating currents, because here voltage is more, E1 dash is more than E2, so the current flows from first machine to the second machine. The current flows from first machine to the second machine. Nothing but this current is flows from this IC is flows from first machine to the second machine. Nothing but the first machine acts as a generator. First machine acts as a generator. Second machine acts as a motor with respect to each other, not with respect to terminal. With respect to terminal, both are generators only, but with respect to each other, see, it is delivering, it is observing. When it is delivering, when it is generator, then it delivers. When it observes, when it is a motor, it will observe. So generator nothing but alternator. Alternator nothing but where we have to operate our alternator in lagging load, where we have to operate our motor in leading load. This is by default actually. So for that, actually this IC, due to this IC only, due to this circulating currents only, due to this synchronizing current only, the machine 1 acts as a generator. Nothing but the synchronizing current comes into picture, comes into action, comes into circuit, which is 90 degrees lagging to the machine 1. Nothing but machine 1 acts as a generator, and which is 90 degrees leading to the machine 2. Nothing but machine 2 acts as a motor. Machine 2 acts as a motor, machine 1 acts as a generator. Like that. So whatever I am saying, that both are actually generator, but with respect to each other, they are like that. So here, these two are the generators only actually, but with respect to each other, they act as a motors and generators. Right now, here the generator first one 90 degrees lagging, nothing but what is the power factor here? 0 power factor lagging here. And what is the power factor here of generator 2? Generator 2, 0 power factor leading here. 0 power factor lagging, nothing but what is the armature reaction? What is the armature reaction for generator 1? The generator 1 is pure demagnetized. Pure demagnetized. Yes or no? Because actually our main field flux is here. Our main field flux is here, for example. Right? So here the machine 1 acts as a generator which is demagnetized, and machine 2 0 power factor leading. Then tell me what the armature reaction in second generator. This is leading, that's why this is pure magnetization. This is pure magnetization, and this is pure demagnetization effect of armature reaction. And observe here, when it is demagnetized, nothing but actually here now my E1 dash is here, but due to this zero power factor lagging, it is demagnetized. Nothing but flux decreases. When flux decreases, automatically EMF decreases. EMF also decreases, yes or no? So EMF decreasing in nature. Once observe here, here the EMF is decreasing from here to here. This is my E1 double dash. This is due to demagnetization. And this E1 dash is due to when excitation changes. As usually, here magnetization will take place. Due to magnetization, flux increases, then EMF also increases. Nothing but actually this is E2, but due to magnetization, this E2 is increased up to E2 dash. E2 dash is due to magnetization. Now see here, after this ISY, when this ISY comes into picture, the E1 dash comes into E1 double dash, and E2 comes into E2 dash. Once observe these two magnitudes are exactly equal. E1 double dash is exactly equals to E2 dash, which is equals to terminal voltage, which is equals to our terminal side voltage. Then what is the circulating current? Zero. What is the disturbance? Zero. There is no any disturbance. Again the parallel operation is going on safely. The two alternators are bring into synchronism. This is the effect of excitation. What happens are here? The effect of excitation is this one. See here, what happened here? When the excitation of the machine 1 increases, ISY comes into picture. This ISY demagnetizes the machine 1 and magnetizes the machine 2 in order to maintain the constant terminal voltage. What happens, sir? In order to maintain the constant terminal voltage. Are you getting or not? Right? This is generally what the effect of excitation. Right. So once see, when excitation changes, synchronizing current comes into action, as well as synchronizing power also comes into action. Let's check the synchronizing active power. Synchronizing active power of the machine 1. Generally, P is nothing but VI cos pi. What is V? For example, E1. And what is I? ISY cos pi. What is the angle between E1 and ISY? E1 and ISY, the angle is 90 degrees. So the PSY is 0, nothing but when disturbances is from excitation side, the synchronizing active power is 0. Sir, only for machine 1 or even for machine 2 also? So let's check for machine 2. PSY2 is equals to E2 ISY, and what is the angle between E2 and ISY? Again 90 degrees. Cos 90 is 0. So you should remember this point. You should remember very, very, very important. What is that? If disturbance from excitation side, from excitation, then the PSY, the synchronizing active power is 0. Nothing but if the disturbance from excitation side, the active power is constant. There is no changes in active power. There is no effect on the active power. This is the very important concept. Let's check the reactive power. See here, QSY1 is equals to EI sine phi. Sine phi nothing but sine theta. What is the theta? 90 degrees. So here the answer is E1 ISY. Nothing but when the disturbance from excitation side, then synchronizing reactive power comes into action. Let's check for machine 2. EI sine again, sine 90 again, that is E2 ISY. Nothing but when the disturbance is from excitation side, disturbance from excitation side, disturbance from excitation, then who comes into action? Reactive power comes into action. See here, this reactive power delivered from the machine 1, this IC delivered from the machine 1, delivering machine 2, observing, delivering, and this is observing. We should remember machine 1 delivering the reactive power, machine 2 observing the reactive power. In order to maintain constant terminal voltage, why the synchronizing reactive power comes into action? Why it is delivering and why it is observing? In order to maintain the constant terminal voltage only. This is our main aim. So, can you tell me, by changing the excitation, what we can maintain? We can maintain the terminal voltage may change. We can maintain the terminal voltage may constant. By changing the excitation, what we can change? What we can change? We can change the terminal voltage. By changing the excitation, we can change the terminal voltage. To control the terminal voltage, which parameter is required? Active power or reactive power? To control the terminal voltage, we require the reactive power. By changing the reactive power, we can control terminal voltage, or by changing the terminal voltage, we can control reactive power. These two are interrelated, reactive power and terminal voltage. So here, by managing reactive power, we can maintain the terminal voltage constant. This is a very important thing in this topic. What is that? The effect of excitation when the prime mover input is constant. So once overview, here at no load condition, both the EMFs are same and terminal voltage also same. With respect to terminal or load, these two are with respect to terminal or load, whatever, these two are in phase to each other, but with respect to each other out of phase. When excitation of the machine 1 increases, EMF increases, ISY comes into action, which is 90 degrees lagging to machine 1, 90 degrees leading to machine 2. Nothing but the ISY is IC or ISY flows from machine 1 to machine 2. This is demagnetized and this is magnetized. Here EMF reduces, here EMF increases. At particular time, at particular point, both are exactly equal, which is equals to terminal voltage. So here terminal voltage is constant. Terminal voltage is constant. So in order to maintain terminal voltage constant, synchronizing reactive power comes into action. This is simply the topic of effect of excitation. Are you getting or not? Are you okay? Now, let's see here. A small topic is there. Let's see here. Is it okay? Right? So, see here. If excitation of machine 1 increases, then what happens? EMF increases at no load condition. This is at no load condition only. Excitation of machine 1 increases, then E1 increases. What happened to E2 actually? There is no changes in E2 actually. Then what happened to VT? VT is also increases because actually VT is equals to E1 plus E2 upon 2, the average of these two. When E1 increases, then automatically terminal voltage also increases. And when E1 increases, there is these two are not same, then the circulating currents comes into action. Circulating currents comes into action. This is the first case. For example, in second case, excitation of machine 2 increases. When excitation of machine 2 increases, EMF of machine 2 increases, EMF of machine 1 is a constant. EMF of machine 1 is exactly constant, no changes. And here the terminal voltage is nothing but E1 plus E2 upon 2 when this is increased, and the terminal voltage is also increases exactly. And when this is increases and this is not changes, then the circulating currents also flows in the circuit. Circulating currents also flows in the circuit. This is the case 2. But now I want to increase my terminal voltage without circulating currents. Can you tell me how? Without circulating currents, I want to increase my terminal voltage. So tell me how we can. So in the third case, I will give you, for example, excitation of machine 1 increases, excitation of machine 2 increases. When these two increases, nothing but E1 increases and E2 increases. If this increment is same in percentage, then E1 and E2 increment is same in percentage, then these two are again equal and the circulating currents are 0. And the terminal voltage E1 plus E2 upon 2, when E1 increases and E2 increases, ultimately terminal voltage increases. Ultimately terminal voltage increases. There is no any difficulty. So this is the third case, excitation of machine 1 and machine 2 increases. And what is the fourth case? If excitation of machine 1 and machine 2 decreases in same percentage, then E1 decreases, E2 decreases. If both are equal, then the circulating currents is equals to 0. And when E1 and E2 both are decreases, then the terminal voltage also decreases. This is the concept, effect of excitation on terminal voltage. At any condition, all these four conditions, there is no change in constant, there is no change in active power. There is a synchronizing active power is 0. But who will comes into action to maintain constant terminal voltage? Here, the synchronizing reactive power comes into action in order to maintain the constant terminal voltage. Here, when excitation of the machine 1 increases, the machine 1 delivers the reactive power to the machine 2. When excitation of the machine 2 increases, the machine 2 delivers the reactive power to the machine 1. If both are increases, there is no change. If both are decreases, there is no change because both are same. There is no circulating currents. If the circulating current is from first to second, if the circulating current is from first to second, what happened? Reactive power from first to second. If the circulating current from second to first, then what happened? Reactive power from second to first. If both are increases same, both are decreases same, there is no circulating currents, there is no flow of reactive power. Are you getting my point? So this is what effect of excitation under no load condition. No load, nothing but the power is zero. Active power is zero. If load is there, active power should be there. If there is no load, there is no active power. Actually, you can think like that only. Yeah, is it clear? Right? We are going to discuss about when two alternators operating in parallel under no load condition, effect of prime mover input when excitation maintaining constant. When my excitation is constant and I am changing my prime mover input, then what happened to the parallel operation set? Let's see here. I told you already, this is parallel operation under no load condition. Under no load condition, E1 is equals to E2 is equals to Vt. And with respect to terminal, both are in phase to each other. Or with respect to each other, for example, this is my E1 and this is my E2, the second EMF. Are you okay? Right. Now, what I am doing here, the prime mover input of machine 1 increases. In this case, I increased my prime mover input for the machine 1. When the prime mover input of the machine 1 increases, then ultimately frequency changes and EMF also changes and phase sequence also changes. Phase shift also changes. What happened? When this is changes, then ultimately the E1 value slightly changes. For example, I am taking, for example, like this, I am taking, this is E1. When the prime mover input of machine 1 increases, the machine 1 changes. For example, this is changes like this. This is my E1 dash. This is my E1 dash. Due to this disturbances, again the circulating currents flows in our circuitry. These circulating currents are how? These circulating currents are actually is like this. This is the circulating currents which are flowing. According to our vector diagram, this ISY in phase with the machine 1 and ISY out of phase with the machine 2. This is the first point. Nothing but, see here the machine 1 ISY in phase with machine 1 and this ISY out of phase with machine 1, nothing but here 0 degrees and here 180 degrees. Nothing but, now here calculate the active power and reactive synchronizing powers. Let's calculate PSY1. Here PSY1 is equals to E1 ISY cos 0. Cos 0 is a 1, so this is E1 and ISY. and calculate the synchronizing active power for machine 2 E2 ISY cos of, what is the angle between these two? Nearly 180 degrees. So 180 is, cos 180 is nothing but -1. So the answer is minus E2 ISY. Nothing but here machine 1 delivering active power, synchronizing active power, and machine 2 observing synchronizing active power. This is delivering the active power and this is observing the active power. See here, minus. Nothing but the machine 1 acts as a generator and machine 2 acts as a motor. Again, same. So here, can you tell me what is synchronizing reactive power? The synchronizing reactive power is equals to E1 ISY sine 0, where sine 0 is equals to 0. What is synchronizing reactive power of machine 2? E2 ISY sine theta. What is theta? 180 degrees, when 180 degrees is equals to 0. Nothing but when disturbance from, can you tell me? Disturbance is from prime mover side. Prime mover side disturbance is there, for example, then the synchronizing reactive power is 0. There is no synchronizing reactive power. We have only synchronizing active powers which are comes into action. Then why this synchronizing active powers comes into action? In order to maintain the constant frequency, because during the parallel operation we should maintain the frequency constant. In order to maintain the constant frequency, the synchronizing active powers comes into picture. Nothing but by changing the prime mover input, what we can change? By changing the prime mover input, we can change frequency. By controlling the frequency, we can control active power. By controlling the active power, we can change the frequency. So the frequency and the active powers are interrelated, and terminal voltage and reactive powers are interrelated. This is the effect of prime mover input on two parallel operation alternators when at no load condition. You have to remember this point. Okay, so here what is the conclusion? What is the conclusion? When the excitation is changes, reactive power will changes. When the prime mover input is changes, active power will changes. In both the cases, synchronizing powers will comes into action. But if the disturbance is from excitation side, synchronizing reactive power comes into action. If the disturbance is from active power side, nothing but prime mover side, then synchronizing active power comes into action. The synchronizing reactive power maintains terminal voltage constant. The synchronizing active power maintains a frequency constant, nothing but speed constant. What is that? Speed. It should maintain the constant speed, then frequency also constant. So this is simply about the parallel operation of two alternators at no load condition I completed. Okay, are you clear? Now they will ask you question. To maintain the or to change the terminal voltage, what we have to change? Option A, prime mover input, or option B, excitation? Tell me. Yeah, by changing the excitation, we can change the terminal voltage. Next one. To change the frequency, what we have to change? Excitation or prime more input? Yeah, exactly. What is that? By changing the prime more input, we can change the frequency. These two are very, very important factors here. Here, when the prime more input of my machine 1 increases, the active power flows from machine 1 to machine 2. That's why machine 1 acts as a generator, machine 2 acts as a motor. If the prime more input of the machine 2 increases, then what happens? The active power flows from second to the first. So second is act as a generator, 2 act as a motor. If both the prime more input increases, then frequency maintained constant. If both the prime more input decreases same, then the frequency maintains constant. This is simply about the effect of prime more input when excitation is maintaining constant. Right? Thank you.